Welcome back. We are going to look into some of the non-idealities that we have in the front end amplifier. So far we have discussed the offset concept with respect to the comparator, and we looked into the solutions, possible solutions that can address that issue. Likewise, of course, in the front end amplifier we have more severe constraints. We have the constraints related to the noise. Along with that, if you have mismatch in the circuit, if you are having offset in the amplifier, how does that affect the characteristics of the overall feedback amplifier that we have built? Along with that, we have discussed in the beginning that the signal specification is going to, it can have a very wide fluctuation in the baseline. So if you remember the discussion in the beginning when we were trying to set the specification of the front end amplifier, we noticed that the baseline can have a huge swing, few hundreds of millivolts, and on top of that you have the tiny signal sitting which is maybe 10 microvolt or 100 microvolt. So the actual signal that you are getting is basically the desired signal, the small peak to peak desired signal sitting on a highly undesired, large undesired signal which needs to be rejected. So this is another non-ideality. This is coming from the signal part that also needs to be addressed. Before that, we also need to check what is the issue with the offset of the front end amplifier itself, whether it is able to whatever design we have made, whether it is able to cope with the offset of the front end amplifier itself. So whatever concept we have applied for offset cancellation in the comparator, we are going to look into the same scheme over here and try to see whether our biasing arrangement and the feedback arrangement that we have for the fully differential operation, whether it is giving us appropriate offset cancellation. So remember, if we do not have the resistive feedback, if we do not have the resistive feedback and suppose you have some DC bias, on the top of that DC bias you have some AC signal coming in. So you have some VCM and then you have the AC signal VD by 2. And likewise on the other side you have another VCM, the common mode, and then you have minus VD by 2, and these two are applied to the positive and negative terminals, and then one of them is having offset. So suppose you are having a V offset. If you do not have the feedback from output to the input, you have controlled the output DC point using common mode feedback. So this is controlled using CMFB circuit. So it is adjusting the common mode at the output, means the V out 1 or V out plus V out minus by 2 will be equal to whatever reference common mode you have, V CM ref. So if I say VO plus and this is VO minus, then I know that VO plus VO minus by 2 will be equal to the VCM ref. This circuit will try to make sure that that is true, but the individual levels VO plus and VO minus, we are not sure about that if this is not having the resistive feedback. And then if I assume that, suppose I try to see first of all what is happening when the input is set to 0, that is how we calculate or observe the effect of offset, right. So we set the input signal to 0, apply the same DC level at both the inputs, and then try to see what is the output. Ideally, if the transistors are fully matched, if you are applying the same DC level VCM to both the inputs, the output DC level will also be exactly same, equal to the common mode level. But if there is a V offset coming in over here and you have the gain A, the VO plus minus VO minus will be different, and then we can say that VO plus minus VO minus will be equal to A times the V offset, because this is, in that case the V offset is going to be effective differential signal between the two inputs, and the common mode circuit can at the most make sure that the VO plus VO minus by 2 is equal to the VCM ref, but the VO plus and VO minus will be different by A times V offset. And if we have offset of even 1 millivolt under that condition, you are having a gain, the overall closed loop gain of this circuit pretty large, say 10 to the power of 4, it can completely saturate the amplifier. Even if you are having a feedback amplifier where you have the feedback circuitry, suppose resistive feedback or capacitive feedback connected, if I assume resistive feedback, in that case once again the offset voltages over here can create large deviation in the output signal, and the outputs can saturate to high or low value even for a small offset voltage over here. So in case we go for the normal operation, suppose that we have a resistive feedback and then we are forcing the output common mode to be having some value. A mismatch over here can suppose you are having a different bias for the input, independent bias of the input with respect to the output. Under that condition, any mismatch in the input side or the mismatch in the devices in the differential amplifier side, it can create mismatch, a significant mismatch in the output levels. For the same DC level, the output will be very different, and despite having same common mode, the actual DC levels at the two drains of the diff amp will be very different, and that can lead to saturation of the output, because you expected that both the outputs of the diff amp or the output stage, if I say so, will be close to VDD by 2, but rather than being at VDD by 2, it is already very far away from VDD by 2. One is closer to ground, another one is closer to VDD. And as a result, the signal swing that you can have is already very much minimized. You cannot go significantly higher or lower, because one side is under DC condition, under 0 input, one side is approaching close to VDD, another side is approaching close to ground, which is not very desirable characteristics. Therefore, independent control of the output common mode and input common mode can create these issues, and if we do that, once again we may have to go for auto zeroing and those kind of techniques to take care of this offset voltage, so that the offset is compensated and we are able to cancel it out. But once again, if you apply auto zeroing in the front end amplifier itself, and you have so much switching noise coming from those transistors, they can once again aggravate the noise considerations. They can make the noise worse. As a result, the resistive feedback that we have for the biasing, we can see that that itself can help us in mitigating the effect of offset to good extent. Let us see what how does it that help us. So, suppose you are having, let us look at the single-ended version. So, if you are having the single-ended version, you are having a large resistor RF that we saw in our example connected over here, and you are having the V offset plus minus, and you are having negative feedback, and then of course you have the capacitors which are implementing the gain. You are having C1, C2, and on the other side, suppose you are having a DC potential. Of course, I am looking at single-ended version, and we if I try to see what is the effect of this particular offset on the output in presence of the RF and C1 and C2, or we can correspondingly look at the fully differential version also and try to see that if there is an offset, what is the effect on the fully differential output. We can keep the offset at any point, and then you have the corresponding capacitive feedback. Now, if I look at this circuit, 0 plus V offset. So, this is DC potential, means some VCM. So, of course, AC point of view we set it to 0, and this is 0 plus V offset. As a result, this is also going to be the same point V offset. And if I look at DC, remember the capacitors do not have any DC paths. So, if I look at the DC biasing, they are not going to play any role, and if this is set to V offset, we can say that since there is no DC path in the capacitor, there is no current flow, the output should automatically be also equal to V offset. If I add DC value, suppose in the actual circuit, of course, you have some DC potential over here. So, V offset plus say VCM, some DC potential with the help of which you have biased the input device. So, that VCM plus V offset comes here, and therefore, you are going to have that VCM plus V offset here, and then VCM plus V offset here. So, as compared to VCM at the output point, you just have VCM plus V offset. So, it is not amplified, V offset is not amplified in this configuration. Whatever offset voltage is present, it is as it is translated to the output. Because of this resistive feedback, the output and the input DC potentials are becoming same. As a result, you do not have amplification at the DC, because offset, I can assume this offset to be very slowly varying, even if it is varies a little bit with temperature, with aging of the device, but it is much slower. I can assume this is DC, and therefore, it is not going to pass through any of these capacitors, and whatever DC potential V offset is appearing over here, V offset plus VCM appears here, and again that DC potential is carried on from to the output. So, there is no current through this capacitor. As a result, the output DC potential in this particular point will be same. Same can be said about this potential. So, if I assume that the output is controlled, you have a VCM at the output, and as a result the differential the overall amplifier output common mode is going to be VCM. So, I can assume that suppose the output, this particular output is set to VCM. As a result, once again, if I see, because of this resistive feedback, you do not have any AC current, any DC current flow through this capacitor. This has to be once again VCM. However, if I take the polarity of the V offset in this fashion, this again has to be VCM, and this therefore becomes VCM plus V offset, and as a result, once again this particular terminal has to be VCM plus V offset. And effectively, if I have the common mode available, common mode feedback available, it will try to make sure that the common mode voltage is same, and therefore it will push it to V offset by 2 and minus V offset by 2, and so there will be a differential swing, and in that case I can model the V offset also as plus minus V offset by 2 on these two terminals. So, I can model this as V offset by 2 over here and minus plus V offset by 2 over here. So, this is just a way of modeling, because I can represent the offset as a V offset by 2 over here as well. So, effectively differential offset between the two terminals remains same. So, if I look at the open loop amplifier's behavior, plus minus the effective difference between the two terminals remains same, which is equal to V offset by 2 and plus V offset by 2 minus V offset by 2, and under that condition the output DC potentials will be once again set. The common mode feedback will force that the output DC potentials remain similar or close to the VCM, and therefore, it will try to push this to VCM plus V offset by 2, VCM minus V offset by 2. Therefore, the difference between the outputs will not be much larger than the V offset. So, you have the difference just given by the V offset corresponding to the effective input referred offset of the amplifier. So, in case of resistive feedback, the offset at the or the difference between the output is just equal to the offset voltage, and therefore, it is not magnifying that offset and saturating the amplifier. So, this resistive feedback in fact is helping us in taking care of the offset also. And we can look at the transfer function also. If you look at the frequency domain transfer function for the feedback, there also you can see that ultimately the effect of offset is getting it is only passing at the DC, and that because of frequency response of this capacitor, anyway the signal response is not affected by this offset. So, for the signal response, once again we have this at the DC source. So, I can forget about this DC source and look at applied signal over here V in, and find out the output signal because of this V in, and then superimpose it on the effect of V offset. So, if you have V offset and V in together, then because of V offset you are having the output DC level shifted to V offset plus VCM. So, slightly different as compared to VCM, you have V offset plus VCM. So, if this few tens of millivolt maybe is 20, 30 millivolt, then only difference is that rather than VDD by 2 you may be having VDD by 2 plus 10, 20 millivolt. Whereas, if you are having the V in applied over here, the output DC points on the two terminals are slightly different. Rather than exactly being VDD by 2, one of them is VDD by 2 plus 10 millivolt, another one is VDD by 2 minus 10 millivolt, and then the AC signal is going to superimpose on those two different DC levels. So, from the point of view of DC, what I can say is that two nodes, the two output nodes, final output, suppose in a common source stage, these voltages rather than being exactly as VCM, this will be VCM plus V offset by 2 and this VCM minus V offset by 2. And then you have the AC signal coming in. So, on the top of that you have A times VD by 2 and minus A times VD by 2. There is a gain, differential gain from input to output. So, this will be the picture. So, the DC level slightly shifting on the two outputs by V offset, and then you have the fully differential operation on the two outputs. So, there is if you are having this resistive feedback, then the only difference is that the DC level will be shifted by a little bit on both sides, not be exactly same, and then you can have the AC signal on the top of this. And if the offset is few millivolts, few tens of millivolts, 50 millivolt is also okay, means we worry so much about the 50 millivolt of DC shift in the output levels. There is not an important concern, because as long as the shift is sufficiently small as compared to the maximum swing they have available, it may not be a very important concern. Maximum swing that is available is say 1 volt peak to peak or larger than that. In case of op amp, we have seen that you can go all the way to 2 volt peak to peak. As compared to that, this shift is, this shift can be few tens of millivolt, 20, 30, 40 millivolt. So, if that is within this limit, we can tolerate that much shift. We may not go for additional steps for cancelling the offset in the front end amplifier, because only thing it is doing here in the resistive feedback configuration, it is leading to some shift in the output DC levels, and that may be few tens of millivolt as compared to the whole swing smaller fraction. As a result, we are not going to apply any additional offset cancellation or auto zeroing scheme for these front end amplifiers to cancel the offset in the main amplifier. So, we can see that if you have the RF present, the offset effect is automatically taken care of. You can also for the AC analysis, that just like we do the transfer function analysis, we can also do the same transfer function analysis for the V offset also, and we have the same high pass filter response coming in, and as a result we know that the offset is the DC value, and the offset value will not be passed on to the signal. So, for example, if I want to see the overall transfer function with respect to V offset, I can say this is the V offset, and with respect to that I have the, if I assume the signal over here is 0 and we have the V offset over here, then we have V offset divided times SC1 is the current flowing into this one, and that multiplied by the Z of this, which is basically 1 upon SC2 parallel RF upon 1 upon SC2 parallel plus RF coming in. This is the output because of the V offset only, and as a result we have once again V offset RF SC1 upon RF SC2 plus 1. This is the output coming, and once again we have the two poles S. We have overall output because of V offset given by S upon, you can say, Z1, and you have 1 plus S upon P1, and out of this which one is smaller. So, if I say RF C1, so RF C1, the 0 Z1 is denoted by the C1 component, and we know that C1 is going to be larger. Therefore, the RF 1 upon RF C1 is going to lie towards lower frequency, whereas the second component R FC2, that is C2 is lower value. Just to have a gain, we know that C1 C2 ratio is greater than 1, C2 is smaller. Therefore, the 1 upon RF C2 component is going to lie towards higher frequency. So, P1 is going to lie towards higher frequency, and as a result the overall transfer function for the V offset to the output is, of course, as we have S approaching 0, then the output is just V offset, and we know that offset this signal itself is only DC, and then as we go towards when we approach say S equal to Z1, when your S is say much greater than so when your S is much greater than P1, then once again you are having this component coming in, and as a result just a minute. So, you have so at S equal to 0, you have the DC value, just a minute. So, you have the S upon Z1 and S upon P1. So, as the S approaches 0, and therefore, you are having the just a minute, there is something problematic. SC1. So, I did the V offset times SC1 multiplied by the parallel combination this, and as a result you have SC2 on this, and as a result if you are having S upon C1, and I am looking at the DC value where S is going much lower than omega equal to 0, it is just a minute. So, if I look at higher frequencies, then of course, this is going to be, So, what I am trying to do is that means as a function of V offset, which is the DC quantity, trying to see how the output is going to vary. So, if I look at omega equal to 0, there I have the offset propagating as it is, but let me see why it is not coming here. So, V offset times SC1 times this feedback path, and therefore, you have the you have C2, and as a result, if I put a omega equal to 0 here, you are getting this 0. Let me see what was the issue. Any error that you can see. RF, this is the current, and that multiplied by the Z, and this is what I have written, and as a result, I have RF SC 2 coming in, and SC1 times RF 1 plus SC2 times RF, and this is the output as a function of V offset, and V in is 0. So, as S is tending to 0, what am I getting output equal to? Let me see. So, if this is the V offset and I have V off means what this has to be V offset, and as a result the output has to be equal to V offset. But what is going on? Let me check this. So, why this transfer function is coming? Sorry. Sorry. No. So, here yes. So, if I see the V offset over here, and the potential over here is V offset times SC1, this is the current, and then you have sorry yes, you have the V offset plus this, sorry. So, you have the overall transfer function coming as 1 plus you have the overall transfer function coming as V offset times 1 plus RF SC1 upon 1 plus RF SC2 plus 1, and as a result, under the denominator I get 2 plus or rather 1 plus RF SC1 plus RF SC2 upon 1 plus RF SC2, and here I know that my C2 is going to be much smaller as compared to C1. I can ignore that 1 plus RF SC1 upon 1 plus RF SC2, and then the corresponding transfer function is going to be simply, if I look at the values, as I said, this is 1 plus S upon Z1 and or Z 1 plus S upon P. So, if I look at this value P and Z, which one is larger? As I said, the RF C1 being the smaller value, that is going to lie at higher frequency. So, the Z1 comes at higher frequency, P1 comes at sorry, the C2 being the smaller one, this lies higher frequency. So, P1 lies at higher frequency, Z1 lies at lower frequency. So, we have going to get Z1 first and then P1 second, and as a result, if I look at the overall response, as the S is going much lower than Z1 as well as P1, this is just 1, therefore, output is equal to V offset. After Z1, you are going to get a decline with S, so 20 dB per decade slope, and after after Z1 you are going to get a plus 20 dB per decade slope, and after you reach P1, then you get S upon Z1 and S upon P1. Once you go much beyond P1, you have S upon Z1 and S upon P1. As a result, both the S cancel out and you are getting P1 upon Z1. So, that is this particular point is going to be given by P1 upon Z1, which is nothing else but C1 upon C2. So, this is P1 upon Z1, which is C1 upon C2. This is our gain for the closed loop, and at the DC, of course, the gain is 1. Therefore, for the V offset, since it is a DC signal, we have to look at the gain of 1. For AC signal, the gain is as expected, as we look for the frequencies which are sufficiently higher than P1. So, we know that while choosing the value of this C2 and RF, we have chosen the RF C2 such that it is able to pass the signal of interest. So, this high pass frequency which is given by the P1 has to be lower than the signal content of interest, and that is how we determine the value of RF over here, if you remember. So, while determining the transfer function, we have anyway seen that this P1 is determined with the help of RF, such that the overall transfer function is able to pass the lowest signal frequency of content, and our offset is sitting over here. For that, the DC gain is just 1 for the feedback configuration. Using the transfer function also, therefore, we can show the same effect, AC signal being able to pass all the signals higher than P1 provided by the cutoff frequency given by RF and C2. Those signals are able to pass, and the offset signal is just experiencing a gain of 1 in the closed loop operation. So, the resistive feedback is able to tackle the offset by just introducing the same difference between the output signal as compared to the offset signal. So, the offset in the signal is taken care of. Another important thing is what is the effect of the chopper. So, we know that if you are putting the chopper in front of the amplifier, chopper and anti-chopper, you have F chop and you have another F chop over here, and you have the amplifier over here, V in, V out. Now, we have seen that this chopper, what is the role of the chopper? It is supposed to transfer the signal towards higher frequency, which is F chop, and the 1 upon F noise of the amplifier remains at lower frequency. Likewise, after the chopping operation, the 1 upon F noise of the amplifier goes to higher frequency, signal comes back to lower frequency. That is the operation we have discussed. The noise, especially the 1 upon F noise, is close to DC. Likewise, the offset, which is over here, you have the V offset also added to this. This is also at DC. So, the chopping is happening before the amplifier, the offset is added to the input port of the amplifier. This is just the offset signal because of the mismatch, and as a result you have the final output coming here, and then we apply the chopping. So, what is the effect of chopping on this DC signal? Once again, we say that the DC signal along with the 1 upon F noise will be shifted to higher frequency. So, in terms of the chopping operation, since we have anyway included the chopping operation, this offset signal was lying at DC, and then of course, you had the 1 upon F noise. So, both these quantities, the 1 upon F noise and the offset signal sitting at DC and close to DC, after the anti chopping operation, this after the second chopper, that is the anti chopping operation, both of them will be getting shifted to the F chop. And the signal is shifted back to the base band or the low frequency content. That was the role of the chopper. The chopper mitigates the effect of the 1 upon F noise, it also mitigates the effect of the offset. So, even if you have a small offset present, it is separated from the signal level, because signal after the first chopper, the signal is at high frequency, the chopping has sent the signal to high frequency, and the offset at this point, the offset is at low frequency DC. After the second chopping, the signal comes back to low frequency, and the DC level along with the 1 upon F noise of the amplifier goes to high frequency F chop. So, they are remaining isolated. So, in terms of AC signal, it does not really come into picture. So, the chopping also takes care of the offset signal, it is allowing separation of the offset from the low frequency DC signal. Of course, we in our case we are not concerned with the DC level of the signal, we are anyway trying to reject the low frequency content, because you are having noise etc., and dynamic offset that we will see just now. But in case of the overall transfer function, it may be important to consider that the offset signal also gets shifted to high frequency because of the chopping operation. The other important non-ideality that we have seen in the example earlier was the dynamic offset, and we need to see how to mitigate this issue of the dynamic offset in our amplifier. So, this is the content of the signal, and remember, when you put the chopper, if you put the chopper before the amplifier, this dynamic offset is present at very low frequency, but it is present before the chopper. Your actual signal is sitting on the top of this dynamic offset. This baseline is fluctuating by large amount, and as a result you are having a huge fluctuation over here. You want to reject this, this is the undesired signal 100 millivolt peak to peak, and the amplifiers can't even process these two together, because if you want to magnify this 10 microvolt to 1 volt, you can see that this will be magnified much larger, therefore you will be clipping the entire waveform. So, therefore, it has to be suppressed, and to do that we need to take care of, we need to add certain things in the amplifier, we need to modify certain schemes in the amplifier, so that this offset or the dynamic offset baseline fluctuation can be suppressed. What is the chopping doing? So, chopping is transferring this baseline fluctuation which is at low frequency along with the signal to high frequency f chop. So, after the first chopper, the signal as well as the baseline fluctuation together will be shifted to high frequency. So, this is not isolated. Chopping is not able to isolate the baseline fluctuation in the signal. Chopping is able to take care of 1 upon f noise, it is able to take care of the DC offset, but not the baseline offset of the baseline drift in the signal. And for that we need to make sure that we have an amplifier scheme which is able to reject this. At high level, that scheme can be represented as a negative feedback loop for this low frequency signal. So, the target is that we add a feedback loop, negative feedback loop, where this low frequency offset or the low frequency dynamic offset is experiencing a strong negative feedback, but the signal is the input signal is not experiencing that feedback. So, basically using a say if you are having a feedback factor beta say given by 1 and the A beta is much larger, therefore, the gain can be at least set to 1. So, for this particular dynamic offset, the gain can be set to 1 if I have a big if I have a strong enough feedback beta equal to 1 in the negative loop, but in that feedback loop I would set the cutoff frequency so low that the actual signal is not able to pass, only the slowly varying dynamic offset, the undesired large amplitude dynamic offset is able to pass. For that, this is the main amplifier, and you have the let me represent the chopper as this rectangle, and I have the anti chopping over here. So, after this I know my signal is going to come back to the original frequency f chop and f chop, and I establish a feedback. This is not feedback in the amplifier, this is feedback in the entire loop. So, after the anti chopping I am putting a feedback network beta, and the negative, this beta is having a very sharp, very low cutoff frequency. So, that it is passing only the slowly varying offset, it is not passing the signal. So, I can represent it, suppose it is the first order, I can represent it as 1 upon 1 plus s upon p. It can be just an RC filter, right. So, for an RC filter, this will be the transfer function, unity gain at low frequency, and at high frequency it is degrading by. So, this just can be an RC filter. So, the output of the signal is coming here, and this is the feedback signal Vf. This is the output signal which I can subtract from the input. So, if I do that, what is the overall effect? So, if I look at the transfer function, suppose the A is having much higher poles. So, the poles in A is much higher, I do not worry about the poles of A. This cutoff frequency of the beta is very low, it is able to pass the dynamic offset. So, for this slowly varying dynamic offset, my overall transfer function of this amplifier will be given by A upon 1 plus A beta. This is our A, which is the closed loop gain of the front end amplifier. This is not the open loop gain. This is our original front end amplifier, where we are having the feedback and you are having the closed loop gain maybe 100. So, this is what we have said. This is the AF, I can say, better call it AF, so as to avoid confusion with the open loop gain. So, 1 plus AF beta. And what we are saying is the poles of the amplifier are at much higher frequency. I am altogether ignoring it. I am concerned with the pole of beta. I am putting a much low frequency low pass pole over here, so that only the dynamic offset is able to pass, only the slowly varying signal is able to pass. The faster input signal, the desired signal, this is not able to pass. As a result, this transfer function will be given by AF upon 1 plus AF beta 1 plus S upon P, which is the pole of this chosen feedback network. Now, what is the effect of this pole on the overall transfer function? This is, I am assuming that AF poles are much higher, I do not even consider that while considering the effect on this low frequency signal. So, what is the effect of this on the overall transfer function? So, I can take it up AF and you have the same function 1 plus s upon p coming over here, and then you have 1 plus s upon p plus af beta coming over here. And then if I take 1 plus a beta out, you have af upon af beta plus 1 times 1 plus s upon p upon 1 plus af beta, sorry, 1 plus s upon 1 plus af beta. And if I assume that af beta is much greater than 1, I can approximate it as this, the first term becomes beta 1 upon beta. So, in the first term is just reduced to 1 upon beta, and the second term you have 1 plus s upon p, and you have 1 plus s upon a beta. This is the overall transfer function we are getting for the low frequency signal, because for the low frequency signal I have assumed that this is able to pass the low frequency signal comfortably. You have very low pass frequency, low cutoff over here. Now, what is this behavior? What is this behavior? If I try to understand this, you have the pole P, and sorry, I also have the P over here, a beta times P. So, in the denominator, of course, when you are bringing it down, you have s upon p times 1 plus a beta. So, you have the P. Now, if I look at the two poles P and a beta times P, a beta is much larger if I assume beta is 1, because if I am assuming a RC filter for the beta, the transfer function is 1 upon 1 plus s upon p. If you just have the beta output signal coming over here, and this is the feedback signal Vf, this is 1, the transfer function is 1 plus s upon p, where p is equal to 1 upon RC. This is what we have for the simple RC filter. This is the output signal being sensed by the beta network, and this is the feedback signal provided. So, I am replacing the beta by a simple RC network. So, the beta for the low frequency signal is simply replaced by the RC network, and in that case the pass band gain is anyway 1 unity, below the pole P the gain is unity. Now, if I look at these two transfer function, what is the overall behavior? This is a beta times p, which is lying at much higher frequency. When you have omega much lower than p, the gain, overall gain for the low frequency signal from this input to the output, for the low frequency dynamic offset, the gain is going to be 1 upon beta if s is much smaller than p. So, where at very low frequency the gain is just 1 upon beta, and then if I am going towards frequencies say much greater than p, then of course, you have the s upon p term coming over here, and as a result you are having the gain increasing. So, the gain starts increasing with s upon p. Till what point it increases? So, you have the frequency a beta times p. After the frequency a beta times p is reached, the overall s factor will be cancelling out, and as a result you will be getting 1 upon beta times a beta, right. That means just a, that is after the frequency a beta times p, the gain of the loop reaches a, which is the desired gain for your signal, right. That means, if you are setting the pole of this low pass filter at p, till the overall transfer function of this loop is going to become a only after a beta times p. So, means if the signal content is higher than a beta times p, the desired signal content is higher than a beta times p, it will be able to pass through this filter, whereas the signal content lower than a beta times p, it will be attenuated as well. So, what I want is that the p should be set such that it is rejecting the low frequency dynamic offset, but at the same time a beta times p should be such that my pass band signal, the desired signal, is able to pass. That is the criteria in setting these 2 points. For example, in our application, if I want to set p is say 0.1 hertz, and the a beta quantity what is the beta? If as I said, beta is 1 for low frequency. So, beta is 1, A is 100. So, 100 times 0.1. So, it is 10 hertz. So, if I keep this at 0.1 hertz, the low pass cutoff frequency of the filter in the feedback 0.1 hertz, this will be 10 hertz. This means the signal content below 10 hertz will also be suppressed. But if we are using, if you are anyway, if you are looking at say the signal content, say you want to pass signals in the range of 1 hertz, or you know that the neural potential signals we are looking at, it can have range up to 0.5 hertz. So, we must make sure that this A beta times P is not very high. So, in that case the A beta will be very much limited, just 5, and therefore, the loop, the A gain that you are having for the main amplifier, that also gets limited. So, we have to make sure that this A beta times P factor is sufficiently low, so that my desired signal sitting at 0.5 hertz or higher, it is able to pass, while the undesired signal sitting at 0.1 hertz or lower is able to be blocked. That becomes challenging, and for that we need to make sure that the transfer function in the feedback path is such that it is able to suppress, or it will able to provide a steeper roll off. So, rather than having a single pole response, I can have a steeper response over here, 2 pole response, and in that case this curve can rise steeper. So, rather than putting just a passive RC filter over here, I would like to put some active filter or higher order filter, so that the steepness of this transfer function can be much stronger. That is what we need to look into. And apart from that, another thing that we need to make sure is that the whatever we are adding over here is not contributing any noise to the main input, because the moment we add any active component over here, any transistor level circuitry over here, if this starts contributing noise to the input, it can create a lot of problem. Therefore, I would like to make sure that this particular component, if you are using any active component over here, it does not add noise to the input point, otherwise it is going to interfere, or it is going to degrade my SNR. So, the design of this loop becomes important, and we have to consider the overall feedback system, where we are trying to pass our desired signal and trying to block our undesired signal with the help of a desired beta factor. So, we need to look into this and try to see that at first of all block level, how do we choose the parameter for this beta network, and second at transistor level, how to implement this connectivity and ensure that while achieving low noise, we are able to reject the desired undesired signal. And for that one option that we would obviously see here is that you can make the beta greater than 1. So, in the feedback, you are using a feedback system where you can make beta greater than 1, then once again we can ensure that the desired signal will be passed sufficiently, whereas the undesired signal will be suppressed strongly. So, we need to see that how to make the beta stronger, maybe greater than 1, while making sure that it is not contributing to noise. So, if the beta here is greater than 1, that means from here to here you are trying to put gain, and the moment you put some active circuit to put a gain, that means again noise contribution is going to come. That is required to keep beta higher and then suppress the undesired signal, but at the same time it should not corrupt the signal with additional noise in the circuitry. So, this loop becomes very critical, and we need to see how to come up with appropriate design catering to the beta requirement, the noise criteria, and cancellation of this wide swing dynamic signal. So, let us stop here and look at this problem of dynamic offset cancellation in more detail in our next module.